Okay, okay, great.
Yeah, I joined. Sorry about that.
No problem. So yeah, so here's our schedule. So first I will give a brief introduction of Wenbin and Guanhua. I'll just basically read your intro you provided yourself. And then I guess I will just leave it all to Wenbin, and Guanhua, you will take over after Wenbin's talk. How about that?
Yeah, that's fine.
Yeah, thanks.
Okay. Yeah, I think we often just start a little bit earlier, right, Hongtu? So maybe I can just start to introduce our speakers. I didn't hear from Hongtu. I will get started. Okay. Welcome to our ARL seminar today. It's our great honor to have Professor Wenbin Lu, my colleague at NC State, to give us a seminar. Dr. Lu obtained his PhD from the Department of Statistics at Columbia University in 2003. His research interests include biostatistics, high-dimensional data analysis, statistical and machine learning methods for precision medicine, and network data analysis. He has published more than 100 papers in various top-tier statistical journals and machine learning journals. His research is partially funded by several grants from the National Institute of Health. He is an associate editor for many top-tier statistical journals. Our discussant today is Professor Guanhua Chen at Department of Biostatistics and Medical Informatics in the University of Wisconsin-Madison. He got his PhD from the University of North Carolina in Chapel Hill in 2014. And his research interests focus on developing statistical learning methods for clinical and biomedical research, with a particular emphasis on the discovery of complex patterns in omics data and electronic health record data to advance precision medicine. So now I will hand over to Wenbin. Wenbin, you can get started.
Okay, let me first share my screen. Make sure. Can you see my screen?
Yes.
Okay, great. And first, I'd like to thank Hongtu for the invitation, and thanks Ray for the introduction. It's my pleasure to give a talk on jump queue learning for optimal interval valued treatment decision rule. This is a recent work, and it's a joint work with my colleague Ray and several of our students. I will first start with a motivating example from the warfarin dosing problems. The warfarin is an oral anticoagulant for prevention of thrombosis and thromboembolism. And in 2004, there are over 30 million prescriptions in US, and the international normalized ratio is a commonly used outcome, which measures the time it takes for blood to clot. And the normal range for INR is usually 0.8 to 1.2 for a healthy person, not using the warfarin. And a target range is 2.0 to 3.0 for people on warfarin therapy. And based on the 2009 consortium, the dose range for patients on the warfarin therapy is from the 10 mg to 100 mg per week. And the higher doses are more effective than lower doses. However, they also may lead to a higher risk of bleeding. So one goal here is to find the individualized decision rule, the IDR, that gives the optimal dose to stabilize the INR for patients on warfarin therapy. And here is our problem settings. We have data xi, ai, and yi. Here, xi is a p-dimensional covariance, and AI is the actual dose received by the patient, and AI is on interval from 0 to A0. And without loss of generality, we just set A0 equal to 1. And Y is the outcome of interest. By convention, the larger the outcome, the better of the treatment. And we have the potential outcome Y star A. That is the outcome that would be observed if a patient were given a dose A. And an individual like decision rule is a function dx which map the covariate space to the dose range, say 0, 1. And the value function of our interest is expectation of the potential outcome y star and the decision rule dx. And the goal here is to find the optimal individual decision rule, that is the d-optimal, which is the decision rule that maximize the value function here. And as usual, when people do in causal inference or doing optimal treatment decisions, we need certain assumptions so that the potential outcome, the value functions can be estimated. The first assumption is commonly used the stable unit treatment value assumption or the consistency assumption. They tell you the observed y equal to the corresponding potential outcome if the actual received dose equal just to that dose A. The second assumption is the no and major confounders assumptions. They tell you given the covariance X, the treatment assignment is independent of all the potential outcomes. The third one is a positivity assumption. They require the propensity score function here, since A is continuous, is the conditional density function of A given X is bounded below by a constant C theta from 0. And given the above assumptions, we can derive the value functions, which is the expectation of this Q function, which is the conditional expectation of Y given X and A. And next, let me give a quick review of the literature for the dose finding problems, or especially for the method for finding the individualized decision rule for optimal dose. The first kind of a class of a popular method is to discretize doses into intervals. For example, Leiber and Zhao 2015, they consider a tree-based method for these dose finding problems. They cluster patients into subgroups and assign a dose for each subgroup based on discretized dose. And also, like in Chen et al. 2018, they consider the doses as ordinal treatment, but they still need to first predetermine the discretization of the dosage range. And other methods also, like for example, include the parametric regression method considered by Rich et al. They just build quadratic interactions between the dose and the covariance, that's the Q functions. And then based on the estimation of Q functions, they derive what is the optimal dose in dose loop. And the more recent development is based on the value search method. For example, the outcome weighted linear method developed by Guanhua, Chen, and his co-authors. Guanhua is today's discussant. And later, our groups extend this method using a kernel-assisted learning to non-parametrically estimate the value function and the dose loop, and then we maximize the estimated value function to derive the optimal dose loop here. But one common limitation here is we just recommend one single dose level for each individual patient. This makes it harder, okay, to implement in practice. And in our work, we made a few contributions. The first one, we proposed the so-called interval valued decision rule, the I2DR, which recommends optimal dose range instead of a single dose for individual patient. So it's an interval recommendation. And the second, since it's an interval recommendation, I2DR gives more options and it's lots more flexible to implement. In addition, in terms of method development, we propose a jump Q-learning method, either based on a parametric regression like linear dose vary coefficient model, or based on non-parametric regression like the deep neural network model. And our estimation procedures is based on a dynamical programming to adaptively determine the number of intervals and the location of the intervals, which is closely related to the literature on estimating the change point models. Later we will see that. And also, we establish the consistency and the convergence rate of the I2DR estimate. And also, we develop a procedure to infer the mean outcome, the value functions, and the estimated optimal policy. Okay, let's start to introduce our method. Let's first start with the value function and the I2DR rule. So our I2DR rule, the interval based optimal decision rule is a function dx, which the input is still a covariance, but the output is an interval on 0, 1. And then given those interval I, we have a prescription functions, the pi star AXI. So they tell you in what kind of for what kind of probability distributions we will assign those within this interval. And since this is a probability density function, we require the pi star when you integrate A on this interval should equal to 1. So we call this prescription function. And then the value functions and our I2DR can be defined as this V pi star D. So it's the Q function when A belong to dx. Dx, that's your recommended interval based on your I2DR rule. Then pi star is the prescription functions on this interval. So when you take integrations of A on this interval, that's our final value functions. Here, if you based on these value functions, nature's thinking is how can I estimate the value function like in the value search estimate, and then to maximize the value functions. But the problem here, they have two problems. The first one is when you do not know what is a pi star, the corresponding value functions may be difficult to estimate non-parametrically. And the second, even you know a non-parametric estimate for V pi star, it still remains difficult to efficiently compute the interval-based optimal decision rule that maximize the estimated value functions. That's the bigger motivations motivate us to consider to propose other method to derive the I2DR rule. Okay, and our method are based on the in our work we consider the following two working model assumptions. The first class of models we call the piecewise functions. So the Q functions is defined on the partitioned intervals. Here, P0 is a finite partition of the 0, 1, those range into a smaller intervals. And on each smaller intervals, we have the Q function, the Q function given by this lower Q, which is only a function X. So in other words, when A belong to these short intervals, the function Q, it does not depend on the dose anymore. So in this sense, it's a constant function. It's only a function of X. So that is the first one, the piecewise function. And for this lowercase q function, we can consider parametric model like linear model. We also can consider non-parametric model, say using the neural network to represent the q function. The second class of models is just consider continuous functions. So the q function is a continuous function in terms of those and the covariance x. For examples, we can consider a parametric model like the dose vary coefficient model. It's in a linear form, but the regression parameter beta may depend on the dose level. And the second, we can just consider a totally non-parametric models, just using a flexible model strategy like the neural network model to model the Q functions. And our method are motivated from the piecewise functions. However, the method can still be applied to this second class of model for continuous functions, and also we start some theories also for these situations. But let's begin using the model 1 as the illustrations for our jump Q-learning and the associate I2DR rule. So if you consider this under model 1 under this kind of partitions, okay, that is the partitions P0 here. Usually we will assume this partition P0 only contain finite number of intervals. And then based on these partitions, we can define our optimal decision rule, which is the interval that give you the maximum, okay, Q functions, right? It's simply given by here. Due to this kind of partitions, we know this optimal decision rule is independent of the corresponding prescription or preference function pi star. And more than that, we can show that the value functions v pi star at this optimal decision rule is always larger or equal to any other decision rule, okay, D, and for any of this preference or prescription function pi star. And for notation simplicity, in the remainder of talk, I just denoted the v pi star just by vd. That is the value function we are interested in. Okay, then we can talking about the ideas of the jump equivalence. And to start with of our procedure, we consider an initial partition P0M of the interval, and we partition the dose range 0, 1 to a smaller refined intervals like the from tau 0, tau 1 to tau m. For examples, we can choose tau k equal to k divided by m, and this m, the initial number of intervals, can diverge with n. Okay, and usually, okay, the choice of m, or the length, this 1 over m, can corresponding to the small unit of increase that a clinician may recommend in practice. And this m, the initial number m, may be large. However, our procedures will adaptively determine the optimal partition p head, which only involves smaller number of intervals based on the jump penalized regressions. In other words, each intervals in our optimal partition p head corresponding to a union of a set of consecutive intervals in your original partitions. And here, the number of intervals in p head has some trade-off. If this number is too large, then you may have too many like shorter intervals. Then it's harder to implement in practice. But if the number is too small, then the corresponding decision rule may not be good. The corresponding value may be small. So it's kind of a trade-off. And here, how we handle this one, we use jump penalized regressions to adaptively select, okay, the optimal number of intervals in the final partition and also the locations of these intervals. Okay, to be specific, let's consider define Bm, which is the set for all possible partitions P, which is derived from the original, the initial partitions. And then we solve, okay, the following optimization problems. So you can see here, we consider all possible partitions from Bm, and then the Q functions defined based on a particular partitions. Then we consider this least square loss, penalize the least square loss functions, and for each interval, and for the treatment assignment belong to this interval, we construct this least square functions yi minus corresponding Q functions, and then add some penalty terms. Here, the first penalty here, the absolute value of P denote the number of intervals, okay, in your partitions, and the absolute value of I, this is denote the length of your intervals. We introduce these two partitions. The first partitions, we introduce these two penalties. The first penalty, this gamma NP, try to control the total number of jumps for the intervals. So we don't want too many, okay, jumps there. So that is one penalty. The second penalty is the penalties on the estimation for theta. Okay, sorry, this is a typo. This is not beta I. Okay, this should be theta I. So that is the regularizations we put on the parameters in the Q functions. This is to prevent overfitting problems when you have a large P. And for fixed partitions, we can solve the optimization problems in this square problems based on different model you assume. For example, so you can use a parametric regression like a linear model, or you can use a non-parametric regression, for example, like a deep learning. And the estimate to I2DR rule is given by d hat x, okay, which is of course defined based on your estimated Q functions on each interval. Then you select the best interval to give the largest Q function estimate. When this argument, if it's not unique, then our d hat x will just output the interval that give you the smallest dose. In other words, this is mainly for the safety concerns. If are all equally effective, we just give the lowest dose as possible. Okay, and then given your estimate I2DR rule, we also can estimate what is the value functions associated with this estimate I2DR rule. And to do this one, given a partition, given an interval, we define the corresponding propensity score function E, which is the probability A belong to this interval given X. So this is like the classical propensity score. We can use in parametric or non-parametric method to estimate E Here we denote it by E hat. With this kind of estimate, we can construct a so-called doubly robust estimate for the value functions. For example, following Zhang et al. 2002 biometrics paper, the value estimate is constructed in this way. So it's a IPW estimate for the y and plus some augmentation terms here. And the reason it's doubly robust is because when either E hat, the propensity score, or the Q hat, the Q function, is consistently estimated, then the corresponding value estimate will be consistent. Okay, next, let me talking about the choice of the Lowercube functions you can use. As I mentioned, you can use parametric regression or non-parametric regression. Here, in our work, we consider two cases. The first case is the linear regression model, the simple model. With the linear regression model, then when you fit this jump Q, it just become the penalized least square problems, then can be easily solved. And the second choice, say here we consider the deep jump Q learning. We use deep neural network to represent the QI function here, but other non-parametric model can maybe also used here. Here, just one illustrations for a neural network with 2 layers and 25 parameters. And when you use this neural network to represent the QI function, when we optimize our loss functions, we can use the stochastic gradient descent method. In particular, in our work, we applied the multiplayer perception regressor for the parameter estimation here. Okay, in terms of implementations, to do that optimizations is quite complicated because you are simultaneously search for the number of interval, the optimal interval locations, and also estimate the Q functions. Here we use a dynamical programming algorithms proposed in change point literature to find the optimal partition p hat. To do this one, we need to define a cost function given by the following term here, and for any interval here, we can define these cost functions. And also we define the set of partitions PR, defined on the interval from 0 to R divided by M with all the grid points like the J divided by M. So the extreme case is BMM, that is the initial partitions BM we considered before. Based on these partitions, we can define the Bellman functions, BR, given in these terms, with a starting point B0 is just defined as a negative gamma n. And now the dynamical program is just rely on the following recursion formulas. So BR is defined through these minimization problems. Using this formula, you can iterate update your B functions here. For example, here is just a kind of like a pseudo algorithms we consider. Given R, we first search the optimal changing point location J that minimize the above Bellman function BR, and the tau R record the corresponding minimizer. Then we can iteratively compute BR and the tau R, and the optimal partition P hat finally is determined by the values stored in the tau functions. So the tau functions stored all the change point locations. And given these partitions, then the set of parameters theta I, either in your linear model, either in your deep neural network model, can be obtained by the corresponding penalized regression problems. And also, when we derive this kind of dynamical programming, we adopt the Pelt method proposed in Killick et al. 2012 to speed up the computations. In other words, when we do this update, we will remove some impossible values, remove them from the set tau. So to accelerate the computation speed, the final computation can achieve the linear computation cost. Okay. And also we needed to do some parameter tunings for our estimation method. In our method, there are a few parameters here we tune. The first one is M, that is the number of initial intervals. We recommend to set M about the same order, like N equal to N divided by some constant C, such that M and N are the same order. And later we did some studies to see the performance for different C, and our findings is not that sensitive to a different choice of C. And for other parameters like gamma n and lambda n, that is the tuning parameter in the two penalty terms. And for the linear JQL, we choose these two parameters simultaneously via cross validations. And we not only that, we also develop some efficient algorithms to compute this cross validation estimates. We don't need to estimate at each of the value of gamma and lambda. We can simultaneously calculate all the estimates together to save times. And also for deep Q-learnings, when we find the MLP regressors, we find that the lambda n is not less than 2, so we just set lambda n equal to 0, but gamma n is chosen based on the cross validations. That is our tuning procedures. And next, let me present some of the theoretical results for our jump Q-learning estimate. And the first one is about the conditions for the initial for all these tuning parameters, like the initial number of partitions, lambda n, gamma n, the corresponding rate. The second conditions is the conditions for your covariate distribution and the outcome distributions. We need to have some this kind of tail conditions for our covariates and outcome. And the third conditions is a commonly used condition we sometimes call the margin conditions. And the condition is given by here. Usually these conditions is required to derive some sharper convergence rate for the value function estimate, for the value function and the estimate optimal decision loop. Okay, and then let's first consider the results for the model 1, the piecewise functions. We first consider we use the linear functions for this Q function, for this piecewise Q function, and our assumptions, we can show that the estimated number of intervals, like the observed p hat, will equal to the true number of the intervals in the true partitions p0, and the estimated changing point will also converge to the true changing point. At a certain rate. Here, the rate is proportional to 1 or n up to some log n factors here. So this establishes the convergence rate of your changing point estimations. Similarly, we can also establish the convergence rate for your the regression coefficients in your linear model. That's theta hat. Also have this log n divided by n rate. So that is for your interval estimation result and the parameter estimation result. The next one, we consider the value function, result. And for value function, then we need the margin condition A6. And then we can establish the corresponding results. We know the optimal value is always bigger than VD hat. So we only need to give an upper bound for this difference. And this difference we establish, they also have the same rate, like log n divided by n rate. And this event will occur with at least 1 minus the n power 1 over n squared, this kind of probabilities. So that is the convergence rate we established for the value function. And next one, we consider the similar results and the deep jump Q-learnings. So now here the Q function is non-parametric and we model through the deep neural network. And to do this one, we need require additional conditions. So we require the functions, the Q functions, the Propan scores belong to the certain class of smooth functions, beta smooth functions. And also we require our estimated Q function are uniformly bounded. This is commonly assumed in the literature to study the neural network estimate. And based on these assumptions, we can study similar results. For example, the first one is the estimation consistency in terms of the number of intervals that's given by here. And for the estimated change point locations, we can still establish the consistency with a certain convergence rate. But this rate is much slower than your linear models. It's n power -2 beta divided by 2 beta plus p up to some log n factors. And not only that, we also established the Q functions, the convergence rate for Q function, and also the rate for the value function estimate. And the result you can see is dominant, just determined by this factor here. So that is the estimation for value functions in the deep Q. And finally, we will also present the inference result for the value estimate. And to do this one, we need to establish this kind of representations. For linear GQL, if the linear model is correctly specified, we can easily, by CM2, we can easily show that the value function and the estimated decision rule equal the value function for the optimal decision, the true optimal decision rule. This difference is only have a small order in power -1/2. But for the deep jump Q-learnings, to establish the same result, we require additional conditions among this beta. Beta is the smoothness of the Q function. Gamma is the parameter in your margin conditions. So we require this condition to hold. Then we can establish similar representations for the value functions. And not only that, we also needed to require the estimations for the propensity score satisfy certain rate, and that is the rate given by here. And this one is easily to achieve if it's the model is given by the parametric model. And but for non-parametric models, for some commonly used non-parametric estimate, this can also be established. Okay, another condition is we require this estimate belong to a class of VC type functions and with these certain orders. So this is a typical condition people assumed in the causal inference literature to establish this asymptotic distribution for the value estimate. Based on these assumptions and a few other regulative conditions, we can establish for both linear jump Q-learning or deep jump Q-learnings, we have the classical root n normalities. In other words, v hat minus the true optimal value will converge in distribution to normal mean zero and sigma square. Here, the v optimal can even be replaced by vd hat based on this asymptotic representation here. Okay, that is give you the way to do inference for value based on these themes. And we also can propose a consistent estimate for the variance term sigma 0. Here, it can easily estimate by this formula. So when you estimate these formulas, a nice thing here you can observe is we do not need to take into account the variations due to the estimation of the propensity score and the Q function. A bigger reason is this double robust estimates. If you have the certain convergence rate for your propensity score function and for your Q functions, they can establish the result, the so-called rate double robustness result, without accounting for the variations, in the nuisance function estimation. So based on the estimated sigma hat, we can construct the confidence intervals for the value function and the estimated optimal value function. Okay, so this is the result for when you have the model, the true model is this really the piecewise functions. And the next part, we extend the result when the true model is not piecewise function, it's a continuous function that we consider in the second class, model 2. And we also study some of the theoretical results. For example, when the true model is the dose vary coefficient model, we require certain smoothness of these coefficients, then we can establish the convergence rate, and these parametric models for the theta estimate and also for value estimate. However, when the model is continuous, there's no underlying these true partitions. So we don't have the change point estimation result for this and this kind of situations. And similarly, if the true model is totally non-parametric and we use a deep neural network to estimate the functions, then we can establish the corresponding result here. And for this case, it's much more challenging than before. We don't have a convergence rate. We only show the consistent result. The estimation for Q function is consistent, and the value function and the estimate the optimal decision rule also converge to the true optimal values, when and go to infinity. So we just established a consistent result. Okay, that's pretty much the theoretical properties we studied for our method. Next, let me quickly present some of the numerical study we did. First one, we consider the settings and the model 1, that is the piecewise functions. We want to study the inference for the value function estimate. So our Y is generated from this Q function. Is a normal distribution with this mean equal given by this Q function and the variance 1. And A is generated from the uniform 0, 1. And our X, just the covariance X, just generated from the normal distributions. Here, first we consider P equal to 4. We have 4 covariance and consider 2 different scenarios for our Q functions. You can see they are all from the piecewise functions. Here in the first examples, we have 3 intervals. On each interval, the Q function is a linear function of your covariance. And for the second scenario, the same interval partitions, but we have nonlinear functions on each interval for the Q functions. So in this case, our partitions, the true partition should be 3 interval, and the changing point here is 0.35 and 0.65 corresponding to the interval partition. And we can calculate what is the optimal value function for this case, which is 1.33. And then we applied our linear jump Q-learning and jump Q-learning and the deep jump Q-learnings for value function estimations. So we report, we consider sample size 200, 400, 800 for both scenario 1 and scenario 2. And for scenario 1, we consider both learnings. But for scenario 2, since the model is nonlinear, we only consider deep jump Q-learning here. So you can see when sample sizes become larger and larger, our estimate become closer and closer to the true optimal values. So they show you the consistency. And also the coverage probabilities constructed based on our asymptotic results also give you correct coverage, the 95% confidence interval, especially when sample size increase. This is both true for the linear jump Q-learning and the deep jump Q-learnings. They give you the same results. And when the model is nonlinear, only deep jump Q-learning works, and the confidence interval, give a nice result here. And also the estimated number of intervals over, I think this 100 replicate, this 500 runs, they are also close to the truth, close to the 3. So you can see the changing point estimations, also the result is correct. In this result, we just set m equal to n divided by 5 and set gamma equal to 0 because the dimension is not that large. We don't need this kind of rich penalties on our parameters. And then we set gamma n by this theoretical rate. That is for the first situation. We studied the value function inference. And the second part, we consider more general models and want to do some comparisons. So the scenario 3 is still piecewise functions, but have a little bit more complicated structures. And scenario 4 is kind of like a very coefficient model. It's not piecewise constant function anymore. It's a completely continuous functions. And the scenario 5, is a quadratic functions. That is functions considered in the original O-learning papers. And we have the corresponding optimal value functions. So you can see for scenario 4 and scenario 5, we do not have optimal partitions. The functions are continuous. And for comparisons for these studies, we consider P equal 20. We consider 20 covariance, and the sample size range from 50 to 800. And we choose m equal n divided by 10. And the gamma and the lambda and the gamma are use the 5-fold cross validation. And we compare our results with outcome weighted learnings based on either linear function or either Gaussian kernel functions. And we did 200 replications. And in the implementation of the outcome weighted learnings, we fix parameter phi equal 0.1 and select other tuning parameter also using the 5-fold cross validations. And this is the result given in the tables. Just recall that scenario 1, 2, 3, the truth is the piecewise constant function, piecewise function. Scenario 4 and 5 are continuous functions. So you can see when the truth is really piecewise functions, the jump Q-learning, either linear jump Q-learning or deep jump Q-learnings, they give much better performance than the outcome weighted learnings because we use this kind of structure, this piecewise constant function structures. And the interesting thing we see here, when sample size is small, the deep jump Q-learnings have much better performance than the linear jump Q-learnings. And then when we move away from the piecewise function to continuous functions, and for these very coefficient models, we still see some big gains for our jump Q learning method. However, for the scenario S5, this when we calculate this kind of quadratic functions, the results are quite comparable, like our jump Q learning method and outcome weighted learning method. They give you very comparable value function estimations. So that is the simulation result here. And the last simulations we show is we want to test the performance of our jump Q length depends on different choice of C. So that's how we set M, right? Our M equal N divided by C. Then we test a different choice of C, and we found at least for the value we choose, like C equal from 6 to 10, the performance are quite consistent. So it's not that sensitive to the choice of C, or in other words, to the choice of the initial number of partitions, as long as this M and N are kind of are in the same orders. Okay, finally, let me go back to the warfarin those data. And here we consider 6 baseline covariates like age, height, weight, gender, and the 2 genotype. And the data consists of 3,848 patients with complete baseline information. And the received warfarin dose is from 10 mg to 100 mg per week, and it's continuous. So we scale the dose into the interval 0 to 1. And for the response, we define y equal to the negative INR minus 2.5, the absolute value. The reason for this one, we want to, the larger y means the better. We want to stabilize the INR range to 2 to 3. So that's why we take this kind of choice for our outcomes. For implementations, we choose M equal N divided by 5 and select the gamma N and the lambda N using 5 cross-validations. And here is the results. I only report the linear jump Q learning here for easy interpretations. And for linear jump Q learnings, we found 2 jump points, and which give you 3 intervals, 3 dose intervals from 0 to 0.05, and 0.05 to 0.17, and 0.17 to 1. And the following tables give you the corresponding estimate, right? Here we consider linear models. So this is the corresponding coefficients in each of the intervals here. And some finding here is patients with genotype VKORC1 as AG or AA should be recommended for lower doses. And the younger patients should be recommended for lower doses. And the male patients should recommend for higher doses. That's based on our dose loop we constructed here. And to visualize the dose loop, we also plot the 3 indexes. This should be theta 1x, theta 2x, theta 3x here. So you can see these are the 3 classes, corresponding to 3 different intervals. So this tell you our suggested dose loop. Okay, I think I can stop here. And finally, I just want to thank this research is supported by NIH from a NIH grant from the National Cancer Institute. And as I mentioned, this is a joint work with my colleague and long-term collaborator, Dr. Rui Song, and our previous students, Chen, and he is currently an assistant professor at London at the London School of Economics, and our current students, Henry Tsai. Thanks for your attention.
Yeah, Guanhua, you're muted.
Right. Okay. So can I share my screen?
I think you should be able to, yeah.
Okay. All right. So I would like to thank, can you see my screens, right?
Yes.
Okay, great. Thank you, Hongchu, for the invitations, and Ray for the introduction, and very nice talk, Wenbin. So today I will lead the discussion of Wenbin's work for jump Q learnings. So first I will kind of provide some summaries of Wenbin's work on my understandings. So I think Wenbin's work, the jump Q learning, basically wants to identify partitions of dose range such that for any dose within the same interval, their Q functions can be approximated using the same models. So for example, if we index the Q function as theta A, then theta A1 will be equal to theta A2 if A1 and A2, these two doses, belongs to the same interval. Or in other words, we can think about this way. For any given x, suppose x is fixed, then Qxa, the Q function, is a function of A, and this jump Q learning, assuming that Qxa is a piecewise constant function of A. And furthermore, for these piecewise constant, the nodes are shared across all x. So that's kind of my understanding for this jump Q learnings. And then based on this assumption, you can see that for scenario 1 to 3, the Q function is indeed piecewise constant. And in scenario 4, the Q function is actually V-shaped. So that essentially means the optimum dose could be only 0 or 1. And then in scenario 5, the Q function is negative parabola. That essentially means your optimal dose can be any value between 0 and 1. So because of that, that explains why in scenario 4, the outcome weighted learning does not work well, because the outcome weighted learning basically assume the optimum dose is continuous, but that works fine for scenario 5. Okay, so the innovation and contribution for the jump Q learning is that it recommends an optimal dose range instead of a single optimal dose. So I think from my limited knowledge, there's no published work really recommending a optimal dose interval. So this is a key contribution of this work. Second is the authors cleverly using the dynamic programming to encourage a parsimonious partition. So they merge these intervals so that it gains interpretability. And furthermore, Wenbin's work provide theoretical results for convergence of the value function and asymptotic distributions, where many other papers, they typically only have the convergence of value function, but not the asymptotic results, or the asymptotic distribution results. And lastly, we can see that the jump Q learning could perform very robust, regardless whether their piecewise constant assumption holds or not. And then I have a few questions I would ask Wenbin's opinion is, first of all, it seems like for the jump Q learning, even though it's very robust, but the existence of the jumps or change point matters. So I wonder if testing the number of change points would help. My second question is that it seems like this framework can be extended to multi-category treatment when there's many categories, but we're assuming for certain category, their treatment effect is similar. So I think that could have some connection to the set valued classification. And I wonder whether Wenbin can kind of comment a little bit about that. And then my third question is whether we could replacing the deep neural network with other non-parametric methods, such as the kernel smoother, so that maybe the Serum 6, the theoretical results may be improved. And then I have other kind of more technical details. Maybe I should ask Wenbin to respond first before I kind of raise further questions.
Okay, yeah. Guanhua, thanks for the very nice discussion of our work, the nice summary. And in terms of the questions, the first questions, I think is in our current work, the number of jump points is through this kind of a penalization method. So it's more like the estimations we adaptively choose the number of the jump points in our dynamical programming. But your proposal, I think, also sounds interesting. So you want to, it's more like whether you need to do this kind of partitions to small intervals. You want to test how many you need for this kind of partitions. right? So I think this is definitely an interesting questions, and I think it's doable, at least in this like the follow like the kind of like a change point literature. After you split the interval, you construct your estimate for the Q function. Based on your estimate for Q function, you want to test whether further split will improve the result or not. So through this one, you can do this sequential testings to decide, okay, the number of intervals to test the number of intervals. I think this is a doable, is interesting and a doable approach, but definitely need more investigation into that. And so that is my first kind of response to here. And the second question is quite interesting. Yeah, to be frank, I haven't thought about this before, but when you have this kind of multi-category treatment, how can you arrange them, make them as like because in the dose finding problems, we have a natural orders, like the small dose to large dose. You can have this natural order. You can do this kind of natural interval partitions, and then using our jump Q learning ideas to more flexibly study the kind of estimations for Q functions. If you have this multi-category treatment, how can you order names in a reasonable way to using this strategy? Then that needs little, I think, a little more careful examining of more careful studies. But I think it is definitely a very interesting questions needed to be considered. And for the third questions, I say the deep neural network is just our choice here. Other non-parametric method can also be used here when you fit this non-parametric component in each of the intervals. Like for example, you mentioned the kernel smoother definitely can be used, especially when the number of predictor, the dimension is small. You can use kernel. You can use a kernel smoother. They can lead to a better estimation rate. That's definitely doable.
Great. So my next three questions more technical. It's like, what about the vanilla Q learning? Like if we use a flexible model to model Q functions, saying how that compared to the jump Q learning.
Yeah.
And then next question is, in the simulation, is like treatment is randomly assigned, and I wonder if the confounding will impact the jump Q learning's performance. And then lastly, I wonder if you can comment a little bit about the computational complexity of the jump Q learning.
Okay, and for the first question here, yeah, you can directly model Q function non-parametrically using the deep neural network or XGBoost method. However, to do this kind of estimations, they cannot give you interval estimations, right? They still give you a single dose recommendations. The reason we do this kind of, we build in this non-parametric this estimation within this dynamic partitions, because we can naturally give you these interval recommendations. So that is the main reasons, okay, we do not consider the non-parametric function for the whole Q function, but through this kind of dynamic partition. And then within each interval, you can estimate either parametric linear or non-parametric models. The whole motivation here is to give you the interval estimations here. Do I address the problem here?
Yeah, it's very clear.
Yeah, and in terms of the confoundings, and in our studies, numerical study, and I think we use this randomization. So this A is independent of X, but the method can be extended to this to allow A depend on X. We can estimate the propensity scores using what parametric or non-parametric models, as long as the estimation rate satisfy that conditions we given in the films, we can still have all this result. So this definitely can improve the observational study, adjusting confounders for treatment assignment. But I'm not sure whether I catch all your questions here or not, or you mean there are some missing confounders or
Yeah, I'm just curious about the usual like measured confounder. Yeah.
Okay, for measured confounders, yeah, we definitely can incorporate through these propensity score estimations. Yeah. Yeah, and finally, for this computation complexities, and this dynamical programming, we use, as I mentioned, we use a pelt method within the dynamical programming. So through these prunings, by removing some impossible this kind of points as the change point, they can accelerate the computation times. They can eventually lead to a linear computational cost that has been shown in that papers. So this is one kind of big things in our proposed jump Q-linears. They can compute quite efficiently. The second part is our cost validation, especially for this linear jump Q-linears. When you fit these square problems at all these tuning parameters, we do not need to do it one by one. We can simultaneously to calculate all these estimates. This also save a lot of computation times. So this partially solve this kind of computation complexities for our considered jump Q-linear problems.
And I think there is a comments in the panelist about the dosing is because may not be a kind of like because a lot of companies may not have that data. Okay, so I think there's a comment saying dose finding is a good dose finding is a good topic for optimal treatment regime. The key stage to determine dose lays in lab and phase 1 trials, but those data are usually considered as commercial secrets and will not be shared. Unless the practice has been changed substantially, it is not practical to apply optimal dose findings, as that create a lot of problem in regulation, manufacture, and the usage of medicine. I wonder if Wenbin could comment a little bit about that.
So here we want to make difference. Here, our dose findings is individual dose findings. I think the question here proposed the so-called dose finding that is in the early stage clinical trials. Usually the data is small, and then in that dose findings, people want to find a safe dose range that apply to everyone, to everybody. So that is more from the effectiveness and the safety concern. It's not an individualized dose finding. It's just find a common dose range, the safe dose range, effective, which is effective and also meet the safe concerns. In our studies, this is more later. We have this kind of, for example, in the warfarin, these studies have a big data, like the large sample size, when people take different doses and then have their outcomes. Then from this kind of data, we want to learn the individualized dose finding. It's not to find a common dose for all the patients. So to do this one, definitely we need a big data, not just like in the early clinical trials. This kind of like, for example, the phase 1 clinical trials only involve a very small number of data. So we do not answer the same kind of questions, and also do not target on the same data applications for our problems.
I mean, if you have any questions in the audience, I mean, feel free to type in here. I can read it out for Wenbin, or we can.
Do we have any other questions from other social media? Yue, can you please check?
Oh, we don't have any questions there.
Okay. So it seems we're all okay for now. So yeah, I would like to thank Wenbin and
There is a question in Q&A session.
oh, sorry.
Yeah, I think the question is pharmaceutical kinetics data is more important for dose finding, and is it possible to combine those with late phase trial data? That's the question.
Yeah, I think this is a very good question. I haven't give a very careful thought about that, but I think definitely okay. It's may be beneficial when combine these two data together, and then but you need when you combine them, you need to find a kind of measures how you effectively use the data from both sides, and from the late phase clinical trial, they like the data we used here and the early trials, and in what kind of measures, okay, you can effectively combine them, and what is the goal of the study, still to derive the individualized dose finding, or you want to use the later phase clinical trial data to improve the early stage findings, or the other way around. So this one, yeah, we need to give a little more thought about the problems and then think about how to combine them. But I think this is definitely an interesting questions to pursue.
Yeah, I want to add a point that I think if the kinetic data, if we can kind of accurately measure some of the biomarkers that can impact that kinetics, then maybe we can make some kind of more reasonable assumption about the Q functions. Maybe that could help the we modeling the apply the jump Q learning model.
Yeah, that's definitely, yeah.
Yeah, I also would like to weigh in. This is exactly why we are doing this type of research for precision medicine. So we really wanted to just go beyond the current one size fits all into, let's say, more adaptive type of medicine procedure. So it would be great if any of the audience or the person who asked the question has some directed experience. We can certainly talk in the future. I guess we're really clear this time. I don't see any more questions in the Q&A and in the chat window and other social media. So I think it's safe to say we're going to just stop here right now. Thanks again for Wenbin and Guanhua for the very interesting, very insightful talk and discussion. And thanks everyone for being here tonight or morning, wherever you are. So we're going to see you in the next ARL seminar. Okay, we're going to stop here. Thank you.
Thank you very much.
Thank you, Ray, for hosting.
Bye.